Okay, so my thanks for sort of letting me invite myself here for a talk. This is some work I've done with my supervisor Carlo. He says hi to everyone that knows him. And essentially what I'm going to be looking at is looking at modified gravity and how we can constrain it, but in particular trying to do it in a model independent way. Okay. So the sort of first half or so has been accepted for publication in CITA, and the second half I hope will be on archive before Christmas, if Carlo actually has time to read it. Okay. So, here we go. So, I'm going to the first half, I'm going to sort of mention some motivation, why you would consider modified gravity, and then why you might consider model independent modified gravity. I'll then look at the parameterisation, which is what I mean by this model independent approach, and then look at some observables and forecast where we might be in maybe 3-4 years' time. Okay. And then, so one of the observables I'm going to use is galaxy cluster counts. Okay. And so this whole first half of the talk has basically a massive caveat to it. Okay. And that's what I'm going to go into a bit more in the second half. Okay. Formalism used for predicting these cluster counts and how well we can expect it to work. Okay. So, why should we consider modified gravity? Why should we go beyond Einstein? He was a pretty smart chap. So, the first thing to mention here is quantum gravity. Now, I don't profess to really know a lot about this, but my point here is that there's regimes in which GR doesn't apply or doesn't mesh well with our other physics. So it might be there's some other theory beyond it. Now, that theory might reduce exactly to GR on the scales we care about, but it might not reduce exactly to GR on the scale that we can. Okay. So, as a cosmologist, this is what I care about. This is our universe pi. So here we have us. Let's get rid of that bit. Oh. Okay. So we're in this 4% here. Okay. And then we think we've got, okay, maybe 22% dark matter floating around. And maybe 74% dark energy. So we think this guy acts a lot like a matter in the universe, but only interacts gravitationally. And then this guy is accelerating the expansion of the universe. And the point here is that we only have gravitational evidence for these guys. So if we only have gravitational evidence for them, maybe we should, maybe it's indicating that we're using the wrong theory of gravity rather than this extra stuff. And then a third, possibly dangerously philosophical point. Well, there we go. It's just that, it's maybe a good idea to do tests that we think we know the answer to. Because we might just be wrong. Okay, so this sort of motivates modified gravity. So what about the model independent approach? So consider the story of Cinderella. Okay? And consider the plight of the prince. So he has a shoe. And he has a country with 6 million people in, and he needs to find out who the shoe fits. So what does he do? He tries the shoe on the first person. Doesn't work. Tries it on the second person. Doesn't work. Tries it on the third person. Slightly better. Tries it on the fourth person. No, that's worse. It could be there for a long time. So what should he do? What he should do is measure the shoe. And you should send out some sort of royal proclamation. If your foot is roughly this size, come to the palace. And hopefully he's now trying the shoe on thousands of people and not millions. So it's a little bit like this. If we have some data in cosmology, we can test F of R gravity against the data, we can test DGP against the data, we can test F of G against the data, we can test Einstein ether against the data, we can test tethers against the data, we can test F of P against the data. Again, we could be there for a long time. So what we want to try and do is get a handle on what the data says about general departures from general relativity. Okay? To see what the footprint of gravity is in the data. So I should probably maybe come up with a few slightly more rigorous reasons for considering the model independent approach. So it doesn't rely on us having the correct model. Okay? And sort of related to that is that certainly from what I can see in the literature, there doesn't seem to be any one modified gravity model that stands head and shoulders above the rest. And It says, look, I solved this, I don't have this problem, I don't have that problem. Okay. The other point to make here is that what I'm going to present isn't a theory of gravity. Okay? It's not the fundamental theory, it's not the answer. But the hope would be that it leads us towards the correct answer. Okay. So, perhaps I should mention, what do I mean by GR equals 1? So, what I mean is I have my FIW metric, here I've specialized for flat, and I've got my scalar perturbations in my potentials. So my psi is my Newtonian potential, sort of governs the acceleration of massive particles, and my phi is my curvature potential. So then we have our Einstein equations, so these are from Fourier space. So we have our Poisson equation, which relates the potential phi to the density in the universe. So rho is the background density, and delta is the sort of co-moving density contrast, which is the density at a point and the velocity. And then we have a second Einstein equation that sometimes we ignore in cosmology, okay? And that's this equation. So what this does is it relates the difference in the two potentials to the anisotropic stress of the species in the universe. Now we think, certainly recently, the anisotropic stress, this guy, is essentially negligible, and so these two potentials are basically the same. So we essentially have one potential, and therefore anything like massive stuff feels that potential, and then photons, anything like that feels both potentials, therefore has a factor of 2. Then what I'm going to do, I'm going to keep the background expansion history the same. Okay? I'm not going to meddle with that. What I'm going to do is I'm going to start playing with these perturbations. Okay? So, what I could do, depending on who you ask, is put an extra parameter into each of those equations I just mentioned. Okay? So we can put a parameter mu in the Poisson equation. I've redefined the Poisson equation to involve the Newtonian potential side. Anyway, so my mu is essentially a time and space dependent Newton's constant. Essentially a time and space dependent strength of gravity. Then I have a second parameter eta, which is the ratio of my two potentials. Okay. And so both of these have the value 1 in GR. And what I'm going to look at is very, very simplified case. But just if I take some redshift, something like 30, and I say at that redshift, I transition to a new value that isn't the GR value of 1, but is some new value, and then see what effect that has on stuff in the universe. Okay. So I should mention that there's a lot of work around these parameterizations. Okay, so I didn't come up with this parameterization. So this is taken from some papers by Gongo Zhao and collaborators, who's actually Simon Fraser when he did this work. There's a big review. This is hundreds of pages done by some guys in the UK. It's a really nice review. There's one bad thing about it, and that's that it came out before my paper, so my paper's not in it. But other than that, it's a really nice review. Okay. The other thing to mention here is that some guys in the UK having a bit of a stroke about these parameterizations. Okay. They claim there's consistency issues and so on. So just be aware that some people don't agree with parameterizing the modified gravity like that. There are other ways of doing it, and essentially different approaches with different pros and cons. So just be aware of it. Okay.
Is there a reason why redshift theory decided to switch this on?
No, and the results I'm going to present are massively sensitive to that. Actually, in the second half will become redshift 50 just for running some embodied simulations, but it doesn't make a massive difference as long as you don't put it before recombination and don't put it too close to the present. You don't get a massive difference. The idea is that if you switch it on too early, then you'll claim that your modified gravity is already ruled out. And so particularly in the case of something like F of R, I think people would claim is that it's some effective field theory that becomes relevant at late times. A little bit like that, which is essentially what you see them do. But yeah, I mean, if you switch it on before recombination, then you get much stronger constraints. Okay, so just to give you an idea that this parameterization I mentioned can capture the features of some models, this is F of R gravity. So in F of R gravity, the mu function has this form, So you see there's some scale dependence and some time dependence, so H is scale factor. And then eta has a very similar form. And basically these constants are fairly set in F of I gravity, and you're left with essentially just one degree of freedom, which is related to the quantum wavelength of the scalar field you value. Okay? So this is just to show you that, okay, you know, this parameterization can capture some models. Okay? Note that there is some time and space dependence here, whereas I'm taking a constant value. So you know, like I say, what I'm doing is very simple. Right, so let's now look at how we can constrain that parameterization. Okay, now again, this has been looked at by lots of different people in the literature. Okay, so nearly any cosmological observable you can name has been mentioned. So you know, weak lensing, CMB, BAO, supernovae, galaxy counts, a lot of stuff's been thrown at this. The key point is to break degeneracies. And what I mean by that is when dealing with your CMB, weak lensing, things like that, your observable is dependent on the sum of the two potentials. Okay? And so it's going to be dependent on both of the modified gravity parameters. So there's going to be some degeneracy. Whereas if you deal with something like the growth of structure, which should only depend on the Newtonian potential of the side, and therefore only on the modified gravity parameter mu, you can hopefully break that degeneracy. Okay? So what I'm going to look at is CMB and weak lensing, and then adding in cluster counts in order to try and break that degeneracy. So the CMB, hopefully everyone in this room knows what the CMB is. I'm quite often talking to non-cosmologists, so it's not always looking. Essentially what I'm going to look at is the power spectrum of just the temperature and isotropies on planet. Okay? And the important part here is the integrated Sachs-Walker effect. Okay? So as the photons travel towards us, they fall into potential wells, and then they leave potential wells. And if that potential well evolves during the time that the photon traverses it, then the blue shift the photon gets from falling in, and the red shift it gets from going out again are different, and so you've changed your spectrum of your CMB. Okay. So this was calculated by the Boltzmann code energy cam, again done by Congo Zhao. Right. Second observable, weak lensing. So we know from GR that gravity bends light. Okay. And so we see these nice Einstein rings and things like this. So weak lensing is happening on a much smaller scale. Okay. So what you're saying here is, well, actually, whenever I see the image of a galaxy, that image could well have been distorted slightly by a gravitational wave. And by slightly, I mean not detectable by the naked eye. Okay. And so if I had some initially circular galaxy, it might appear to me to be smaller or bigger, or it might get sheared, so it might appear a little. Okay? And again, this depends on some of the two potentials. We're dealing with photon GeV. Now, because this is such a small effect, I can't look at one galaxy. I can't learn anything from looking at one galaxy. But what I can do is I can look at the patterns of these things on the sky, okay? And look at the statistics of that, and that gives me an idea of what my potentials look like in my universe. Okay, so at this point I should say everything I've said so far was done by other people. Okay. I've done analysis with CMB and weak lensing, but other people did it first. So what I've added in is cluster counts. So, what are galaxy clusters? So we think they're sort of large dark matter halos full of hot gas, the odd galaxy, blah blah blah. Okay. And we hope that the number of clusters at different redshifts is very sensitive to psi over, okay? Just the Newtonian potential. And so what we do is we have these objects called mass functions, and what they do is they take our linear matter power spectrum, and then they give us out our predicted number of cluster counts. Okay? Now, I'm going to go into these in a bit more detail in the second half, okay? Because it's not obvious we can use our current mass functions in modified gravity, but don't worry about that at the moment. And so what we do when we're dealing with a survey is we have something like this. So we have a limiting mass, which is the smallest mass of cluster that our survey can see. And so we've got our number density of objects of mass greater than that comes from integrating our mass function, our prescription, from that limiting mass function. Okay. Just very simply what the observation is. Now, to give you an idea how potentially sensitive this is as a probe, So this is number of objects, total number of objects at different redshifts for some survey. The details of the survey don't matter. And in black is my curve for GR lambda CA. So what I'm going to do is I'm going to say, okay, at redshift of 30, I'm going to increase Newton's constant by 10%. 10% change, I pretty much get an order of magnitude increase in my number of clusters. This is potentially very sensitive to a change. Right. So, what I've presented so far is quite an optimistic view of cluster counts. Okay? So presented them as, yeah, we know about them, we can predict them, blah, blah, blah. So in fact, that's quite an optimistic view of clusters. Okay? And in fact, the big thing with clusters is that although their mass is what you care about, you never observe the mass of a cluster. You observe its X-ray temperature. You observe its sinusoidal its flux, whatever it is. Okay. And so, if the scatter in that relationship between the mass and what you actually observe, then that's going to affect your constraints. So we want to include this in the analysis. Okay. So I have to be honest, I've been explaining this incredibly badly over the past week or so. So let me see how I do today. So imagine you have a survey that says you can see every cluster above 10 to the 14.4 solar masses. And what you're saying is that you put a sharp break in here. Sorry, this curve coming down here is my mass function. So a number density of objects of different masses. So what I'm saying is my survey can see everything above this mass. Essentially, we put a sharp break in here, and I see all the clusters this side of the line, and I don't see anyone on that side. But in actual fact, if what I should do for my my experiment is I should say, well, actually, there's some scatter. Okay? There's some relationship between what I observe and the mass of the cluster, and there's some scatter in that relationship. Okay? And I need to take that into account. So, for example, that same survey I just mentioned might actually follow a curve a bit like this. So, I don't see these light grey clusters here that I thought I would observe, but then I do see these extra ones here because of this relationship.
So what is this? So, well, two questions. So what is this mass function? Where does that come from? Second.
I'm going to talk about mass functions a bit more in the second half of the talk. Essentially, what it is it's a formula, and you put your linear mass and power spectrum in and get out your number of objects of different masses.
But what is this formula based?
I'll go into a bit in that in the second half.
And the second, so what, because there is a connection between what you observe and, so why do you see that function is formula?
Right, so say I'm looking at, I don't know, an SN survey, and I claim that my survey can detect a change to the CFD sky of a certain flux. Okay. Now, naively, you would associate that flux exactly to a particular mass of object. And you would say that therefore your survey could see every object of that mass or upwards. But actually that's not true, because it's not an exact relationship, there's some scatter. So for a given change in flux, that object could have a mass in a certain range. Okay. And it's just trying to take that into account. So that's why you see, I'll show you on the next slide, it's a little bit more quantitative. But instead of having essentially a sharp cutoff here, I'm saying, well, actually, there's some relationship. So what Beamer and Hugh did was they said, okay, so consider the probability of assigning a mass, the observed mass, to an object that has a true mass m to be given by a Gaussian in the log of the mass. Okay. So we have this. And so then when I ask what my survey sees, I have some limiting mass which corresponds to my survey. When I ask what my survey sees, instead of having essentially just this first bit, limiting mass upwards, that I had before, I now have this extra term. So one thing is just to include this in the analysis. However, what if we've got this relationship wrong? So this sigma, so parameterizes the scatter in this relationship. Okay. We think we've maybe got a good idea of that, but if we've got it wrong, it's going to affect our constraints. So then what I'm going to do, I'm going to treat this sigma as another parameter. Okay. Just to try and be consistent with how I do my clusters and try and be a bit more aware of the uncertainties associated. So, this is the telescope in Chile that I keep forgetting the name of, which is really bad. But this is going to be where the dark energy survey is carried out. Okay? The dark energy survey, I think, should start taking data next year. And that's what I'm going to use for my sort of template beat lensing survey. Oh, one at a time. So, here I have Planck. That's what I'm going to use for my temperature anisotropies piece for CFB. Here it's floating in front of the W night sky. The other thing I'm going to use Planck for is my cluster catalog. Okay, so essentially when we look at our CMB, in some sense we get a cluster catalog for free through the Sun Nips Observatory. So what this is, as the photons are traveling towards us, they go into a cluster, they bounce off the hot electrons, we can now see the cluster in our microwave sky. Okay. The really nice thing about the SZ effect is it has a very particular frequency dependence. So around 217 gigahertz, you don't really see anything. And then below that you see a cold spot, and above that a hot spot. Okay. And so if I look at my microwave sky at different frequencies, I can hopefully say, look, there's a cluster, there's a cluster, there's a cluster. Okay. So hopefully this is quite a nice way to find my galaxy cluster. Right, so I'm going to forecast Planck and DES. I'm going to do that with a Fisher matrix. So this is nice and simple. Essentially what I'm doing is I'm looking at how my observables change as I vary my parameters and comparing that to the noise on the experiment. So I compare these two things. If my observables change quickly as my parameters change and my noise is low, I should be able to put quite good constraints on the parameters. And if my observables don't change much as I vary my parameters and my noise is quite large, then I'm going to struggle to constrain the parameters. So that's essentially what this is saying. Something we came across was if you don't cross-correlate the CMB and the weak lensing, then you do lose information. Right, so where might we be in 3-4 years' time when we've got data from these surveys? So this is mu, strength of gravity, our effective Newton's constant, and this is eta, a ratio of our two potentials. So just consider the red curve at the moment. Okay? So the red curve has no clusters in it. So it's just weak lensing from DES and CMB from Planck. And you can see the way, maybe 3-4% constraints at 1 sigma on eta, and then, maybe getting towards a percent constraints on our strength of gravity. So that's looking fairly promising. Now, the green curve is when we add in our cluster counts. So we can see that, okay, it does improve things. It seems to be breaking this degeneracy that I claimed was there. Okay? And we are getting, tiny constraints. So this is a good thing. The yellow curve is when I take into account those uncertainties I mentioned about the cluster counts. Okay? When I take into account the scatter in the mass observable relationship and marginalize over it, I lose some of my constraint. But it's still better than the red curve. Okay? And the hope would be the more and more we learn about clusters, this yellow curve is going to tend towards the green curve, and we recover all that constraint. Okay?
This was also over the yellow parameters also, like CMB?
Yeah. Everything else is the marginalized. Well, we don't include all the cosmological parameters in this. There's a bit of hand waving and saying things like, okay, hopefully tau will be constrained by polarization and stuff like that. The two that are most degenerate with these two are omega matter and the scalar aperture. Okay. So this is sort of a little summary of this first bit of the talk. So combining experiments hopefully allows us to constrain the model independent quantified gravity. Okay, this is good. And okay, people knew that before I came along, but then adding cluster counts into the mix does seem down. Okay. So now I need to go into this massive caveat I mentioned. Okay. So this was a little bit write a paper, and then I now need to write another one to justify the first one.
Yeah, so basically you're saying that all of them, when you modify the theories, you can just clarify by the deviation from the side and phi.
Right, so the answer to that question is quite long and long. And depends exactly what you're trying to achieve. So to start with, I've only considered scalar perturbations. But generally, if you consider scalar perturbations, you can get away with, two free functions. Okay. Now in principle they are free functions. They're arbitrary functions of time and space, but what I've treated them with is very simple. That said, once you start introducing scale dependence, you tend to get better constraint solving. And again, the guys at the time were great that I've looked at doing principal component analysis on the forecast, and that does help. Now, the question of what exactly these parameters mean when you relate back to the model comes back to what I was saying about the guys in the UK, Costas Cordes, Pedro Ferreira, and so on. They're arguing that these parameters don't go back very nicely into talking about your model. So it depends what you're trying to do. So you can always, you can always go out and measure the density and measure the potential and look at the ratio between them. You can always do that, which isn't necessarily the same as claiming you've got a modified Boltzmann equation. So in doing this, we're sort of parameterizing the solution of what the modified gravity's done, what the initial conditions were, and looked at the end result, rather than parameterizing theories, if that makes sense.
But then, like, even in geometry, you can have sine phi and
yes, exactly. Exactly.
Yeah, so in this case, won't that also be small, or it should be minuscule?
Yeah, unless there's sort of more neutrinos than we think, then that should be fine for the kind of redshifts I'm talking about. Okay, so yeah, this massive caveat. I use these mass functions, these formulae that take my linear matter path spectrum, give me my number of objects of different masses. Now they're calibrated for lambda CDM GI cosmologies. Can I use them in modified gravity? I don't know. Let's find out. So this sort of comes from Untitled Chapter way back. So, ask yourself the question: if someone gave me a linear matter path spectrum and asked me how many clusters of a certain mass I have in my universe, how would you do it? So what these guys said, well, okay, let's smooth that linear density field, okay, on a scale R, some scale R. And because of our background density, that scale relates to some mass of object. Okay. Now what we can do is we can say, right, all of space where the density field is above some threshold, I'll go a bit more into that in a second, but all of space where this smooth density field has a value above some threshold is in collapsed objects. Okay? And then I can sort of associate then that volume of space with objects above the mass of the smoothing scale. Okay? So I have a picture. I'm really sorry. This was stolen off Google because I'm rubbish at drawing, and I'm not quite sure who's from. If you're in the room, I'm really sorry. So this is my threshold. This is my linear density of delta smooth on some scale, and this is my threshold. So this very wiggly curve. If we look, okay, so these black bits, we're saying we can associate those with collapsed objects of mass greater than the mass corresponding to what was used to smooth this thing. Okay. And then I can smooth my curve on a larger scale and therefore a bigger mass. And this is the dash curve here, and you see less of that curve is above the threshold. Okay. So that difference in volumes I can associate to collapsed objects of mass between the mass associated with this smoothing scale and the mass associated with this smoothing scale. So this threshold, this delta C, this threshold, is the linear density contrast for collapse of a spherical presentation. Okay? So if in my expanding universe, if I put in this sort of ball of matter which has a density above the background density, okay, then it will collapse. It's a really nice calculation of GI, and it's 1.686. Okay. For an omega matter equals 1 flat universe. Okay. So they took this idea and they said, okay, right. So let's apply this, and you apply the chain rule something like 7 times, and you get this. So you see my number density of objects of a given mass at a particular redshift is related to, so I've got my background density, I've got the mass of objects I'm talking about, and sigma is my linear matter power spectrum smoothed on the scale R corresponding to a mass M. So I can predict that. Okay, so it turns out that the pressure vector approach isn't as accurate as people would hope. So Shest and Tormod extended it to include ellipsoidal collapse, and this does better. So if I show you a little plot. This is for some n-body simulation. Okay? So some volume of space, the total number of clusters I see at different masses. Okay? So the black curve is pressure vector, and the blue curve is Shest Tormod. This purple, magenta, pink, whatever color you want to call it curve is calibrated to n-body simulations. Okay? And so we can see that the pressure vector predicts too many low mass objects and too few high mass objects. Okay? But the Shest Tormod one is doing it. So what people did was they said, okay, they said, let's take the sort of functional forms of these guys. Okay? Let's not worry too much about the numbers, but let's take the functional forms. Okay? And we can use these to fit n-body simulations. We can run n-body simulations for different cosmological parameters and so on and so on. And then the claim is, depending on exactly who you speak to, these mass functions are accurate to sort of 5–10% as the cosmological parameters are better. So that looks quite promising. I think at 10% it does include some varying W cosmologies, varying the equation of state dynamics. So it looks relatively good. But do they work in modified gravity? So to find out the answer, you're going to have to run some n-body simulations. So I've used Volker Springel's code, Gadget 2. This computes gravity in a tree PM approach. So 2 different ways on 2 different scales. So on large scales, you put a grid down, you assign particles essentially in some way to the grid points they're nearest, and then so you've got this discrete density field, Fourier transform it, Volker uncle, you've got a gravitational potential, and so on and so on. On smaller scales, you do it a bit more directly. But in a slightly clever way. So say this is the particle, but I want to know the force on this particle. So if a particle's nearby, I'm going to have to compute that fairly directly. Okay, I can't cheat. But if I have several particles further away that are reasonably close together, I can sort of treat them at their center of mass and treat the effect on this guy. The computing of it is more complicated than that, but that's essentially what you're doing. So what I'm going to do is I'm going to modify the gravitational force in both of these parts. Obviously, we want to potentially vary it on the scales by essentially just putting in the mu parameter. So I'm going to change gravity I'm going to change Newton's constant by a certain amount. Okay. Something to mention here that I'm only recently starting to appreciate is it's not obvious that this mu is necessarily related to the mu of the first part, because one is our linear GR regime and one's our Newtonian regime. It's not necessarily obvious that it's the same thing going on. Okay. The other thing I'm going to introduce here is a screening scale. So this is something that occurs in modified gravity theories, and essentially it's a length below which you get GR. So you only see the modifications above the center. So the reason for this is that if you start messing around with gravity because you want to change cosmology, you're going to run into solar system constraints. Okay. So what you need is some environmental dependence of your theory of gravity, so that in dense environments like the solar system, you get back to GR, and in less dense environments, sort of more cosmological environments, then you get a modification. Okay? And there's various mechanisms for doing this in the literature, things like the Einstein mechanism and the comedian mechanism. So in FOR, you tend to get the comedian as an example. It comes into the nonlinear equations. Okay? So if you did linear theory FOR, you wouldn't see this. But once you start dealing with the nonlinear part, then you start seeing the screen. And now I want to continue this sort of model independent approach. So what I'm going to do is I'm just going to put in a length, okay, something like a megapartic. And I'm going to say, okay, below this length, I don't change GR. Above this length, I do change GR. So once I've run my n-body simulations, I need to find my clusters in them. Now I have to admit, as a naive PhD student, I was surprised by how difficult a problem this was. So you have these particles, these big masses floating around, you know where they are in this volume, which is the output of your simulation. How do you find clusters there? Okay. So from what I can see, there's 2 main approaches in the literature. So spherical over density says, okay, well, I'm going to find spheres in the simulation such that the average density in these spheres is 200 times the background density. Okay? Another approach is the friends-of-friends approach, which works on a length. So it says if I can find the particles that are all near each other according to some length, then maybe I've got a bound halo. Okay? So I'm afraid I have another picture shamelessly stolen. So again, if the author's in the room, I'm really sorry. So imagine this small linking length. So I'm going to take this small linking length, I'm going to throw it at my particles and say, what do I find? Well, I find that these two are bound together and these three are bound together. And then I can make my linking length a bit bigger. I can make it maybe this one, and I find that, okay, this is a halo, but these guys are all still not part of a halo, and then this is a halo. Okay? So I think the thought originally was that a given linking length would correspond to a given sort of isodensity contour. So there'd be quite a strong relationship between the two algorithms. Now it seems like this is only true for spherical halos. Okay, you get quite a strong relationship between the two for spherical halos, but it breaks down for non-spherical halos. Okay? I think from what I've read, something like 20% of halos in simulations and in the real world are really not spherical. So I'm going to use friends of friends because it deals with the non-spherical ones better. Okay, right. So I modify my simulations. I can find halos in them. Let's do some runs. So I'm going to do sort of 10 realizations of a lambda CDM, GR box, and then 2 sets of runs to modify gravity. Okay. One of those is going to have the screening scale, and one of those isn't going to have the screening scale. So in one of them, gravity is modified on all scales, and in one of them it's only modified above a certain density. And my mu I'm going to change by about 5%. So my Newton's constant is going to be 5%. This is details of my embodied simulation. 16, 17 million cold dark matter particles, Boltzmann length 400 megaparsecs, and the Starling energy to 50. And then this is the mass function in the literature. It's calibrated to embodied simulations that I'm going to compare to. So for each of these runs, I can get the power spectrum, essentially the sigma, and I can say, okay, how well does this prediction work for GR? How well does it work for modifying gravity? And then how well does it work for the screening? So I'll just show you some power spectra. So here the black curve is lambda CDM GR, and the blue curve is for the 5% change in modified gravity. Okay? Ignore the red curve for a moment. Right. So what do we find? So we managed to reproduce the results for GR and lambda CDM, find the same sort of number of objects as everyone else, which is always a good thing. And surprisingly enough, you tend to find more clusters for stronger gravity. Right, so let me show you total number of counts. So this is total number of objects we found in our simulation of different masses. Okay, so this is 10 to the 13, 10 to the 14, and 10 to the 15 small masses. Okay. So black curve is GR. The arrow bars are, so the points are the average of the 10 runs, and then the arrow bars give you an idea of the sample variance. So black is GR. Blue is a 5% change in modified gravity, 5% change in gravity, and green is with the screening scale. So we can see that, okay, we get more objects in modified gravity, and particularly at the high mass end, okay, we should maybe expect that. With the screening scale, particularly, it's true for modified gravity, but it's more true when the screening scale.
How was the normalization made for the, what did you decide?
I put the same initial power spectrum into the embodied simulation. So the sigma rate will be different in his models.
Right, so if you adjust sigma, just so that it's, for example.
I haven't looked at doing that. You would, I'd have to get back to you. That's something we're thinking about doing.
So what's going to happen is that it's going to come down around in between those two lines. It'll probably come into be a reasonable match there, and it will maybe go back, because that sigma is a controller of a certain mass distribution in the cluster. Right?
Yeah.
So it's basically mass.
Yeah.
And I don't think it gets modified by modifying gravity. It's not an efficient. That could be wrong. I mean, can you actually write sigma A as a function of G, and then as G varies, in other words, is there
in
a
these
running
models
like
you've got
D log
a
sigma
bigger
8 by D log G or something like that?
Yeah, I would hesitate to do that because this mu is, it's not obvious you can claim
It's not just a
actually
uniform scale, right?
but, so you've got bigger growth and perturbations. So I mean, your sigma rate will be different as you change these things. But, right, so I have to think about this. People have done this. So people have looked at some specific models and run n-body simulations and tried to match the final power spectrum. And I haven't properly looked at how their cluster counts change, so I have to get back. Anyway, so around this end, we actually get, particularly with the screening scale, we actually get fewer clusters than you would in GR. Okay? Because if you think, as your structure forms, you form small objects and they evolve into bigger objects, then in some sense with the screening scale, you've got two sort of laws of gravity operating. And so your objects here at an earlier redshift have been made into these objects quicker than the objects that are smaller mass have evolved into the objects here. I claim. I need to look more at the redshift sort of evolution of stuff, but I claim. Okay. So we maybe see more clusters for the same initial position. So how does the mass function work? That's the question we want to answer here. So here we go. So what I've done is I've taken those that previous plot and divided the counts for each of the three kinds of run by the respective prediction. Okay. So these black lines give you an idea of the sample variance. Let me get this right. Black circles are GR. So that's these guys here. So this prediction looks like it works quite well. Okay. Then these blue points are modified gravity, 5% change to gravity across all scales. And again, this mass function seems to do quite well. Now, once we introduce, the screening scale into the simulation, we've got a problem. Because that screening scale I told you doesn't show up in the linear matter power spectrum. So I'm using the same prediction for the green points as I am for the blue points. So the prediction fails miserably. It's not even close. Okay. So maybe I've got a problem here. So what I'm going to do is I'm going to cheat. I'm going to say, well actually, since all I've done is put in this this length scale, the screening scale by hand, then actually what I can do is I can put it in by hand into the linear matter power spectrum as well. So that's what the red curve is. So the red curve is for the 5% change to gravity above 1 megapascal. And so as expected, you sort of, on smaller scales it looks like GR, and on larger scales it looks like 1 megapascal. So this is a bit of a cheat because in a real model it would never occur in the linear matter power spectrum. But let's see what happens. So, these green ones are the ones we had before with the old prediction. Now we're going to put in the new prediction and we get these red ones. So actually that's starting to look quite nice. It's starting to look like it might work. Okay. But how far you can justify what we've done is a different question. Okay. So
can you flash back? Are they on the same scale? Yeah, no, they aren't the same. So
yeah, the green are the same, right?
No, the green are the same, but it's the red and then 1.05 with the...
Oh no, you're not expecting that. You're not expecting that.
No, I know. It's just I'm interested in the level of constructs.
Yeah. I mean, I haven't come up with a particularly quantitative analysis of how well prediction works, but by eye I would argue that all three are better. Okay, so we should maybe sort of conclude this sort of second bit. So mass functions are useful objects for predicting cluster counts. Great, we already knew that. They kind of seem to work for small departures from GR. Okay? In this case, as long as the screening scale somehow appears in your linear matter power spectrum. So sort of more generally, perhaps the claim would be that as long as you get the same behavior in your linear matter-power spectrum as your non-linear matter-power spectrum, then you don't need to run n-body simulations every time you have a new theory of gravity, as long as it's reasonably close to Q. Now the work I've done here is one, very simple and very idealized, and two, not as extensive as it needs to be. So this is very much a hypothesis that we haven't ruled out, rather than something that has a massive amount of evidence for it. So one interesting thing that to come next is, okay, well, let's put some scale dependence into that mu parameter and see if our mass functions still work now. So if we say our mu goes as, I don't know, k squared or whatever you want to make it go as, that will obviously start changing the shape. Is your mass function still going to work in that case? I don't know. It's not going to. Anyway, that's me. Oh, wow, was that?
Unfortunately, I injected myself late, so the F, is this within the F bar context, or a phi squared r, or just a phenomenon?
Yeah, these are phenomenal parameterizations. So you have
okay.
There we go. So you have essentially got extra parameters with your Einstein equation.
But if it enters in such a way, then it has to be at some level self-consistent with
Yes.
the perturbation equations that you're solving.
Yeah, so this, if you rewrote this modification as an effective energy momentum tensor, it would satisfy energy momentum conservation. And on super horizon scales, it satisfies.
Say that again, as an effective energy momentum tensor.
Yes.
So you mean you're treating the gravity side the same, and you're putting in a effective coupling?
No, it's just, so when you write down a modification to GR, you can obviously modify either side. And you would want anything you write down as a change to gravity, essentially because of your Bianchi density, you would want it, if you wrote it as an effective stress energy tensor, you would want it to satisfy energy momentum conservation. So it does that. The other thing this does is you have your super horizon consistency.
But mu is entering as a fix. It's got no dynamics, no response. You're just putting it in dynamic.
Yeah, exactly. And the idea is for surveys is to put it in essentially pixels. So you bin it in redshift and in K, and try and constrain those with surveys. And the guys at Simon Fraser, Lamont Bogosian, and postdoc on Without and so on have done sort of principal component analysis to try and understand which sort of redshift bins and which shape dependencies would be best constrained by different surveys. But in what I've done is very simple. What I've done is very simple.
But there's absolutely no feedback with delta with mu.
No. And I think that sort of comes back to what Costas Gordis and Pedro Ferrer are saying. They don't like this way of parameterizing multi-gravity. They say that they don't like it when you then start talking, when you want to go back to more and start talking about what it means to them. I think it's their issue. So they do everything a different way. They always sort of parameterize things at a much earlier stage and then say, well, what's it look like? But the problem with that approach is I think you need to, it's a swings and roundabouts thing. You're gaining and losing different things. But I think the problem with that approach is that you need to start making assumptions about the classes of theories you've got before you can get anywhere. And so, as I said, although you sort of interpret the mu here as an effect of Newton's constant, you're not necessarily saying that an equation of motion of your new theory of gravity is that quantum equation then. You're not necessarily saying that. You can always go out at any point in time and go out and measure your potential and measure your density and sort of look at the relationship between them. So, which isn't the same thing as claiming that this is actually an equation of motion. So this is, so I'm trying to get my head around this at the moment, but essentially this is, you're parameterizing the solution. So given some initial conditions and some mu and so on, you're parameterizing then what your cosmological observables look like. So you could write massive neutrinos, quintessence, whatever you wanted. You could write that in terms of this mu and eta somewhere.
I'm not sure that's true. So, but can I not? I don't know this, but can't I mean, the key thing about modified gravity, pi squared r, and all of that is that you formally transform it from the evolving Newton's parameter to one in which the Newton's parameter is constant, but it has more complex couplings with matter. I gather that's what you're basically talking about. So that has an equation, like a formal factor. Starting with that might be a better approach because it at least can have feedback in terms of what the matter does.
I think that might be related to what Costas and Petri do.
Yeah, so, let me put it another way. What you would probably like to do is you'd like to start with the action, which you could then write the fluid action or cold dark matter action or whatever. And then you've got whatever the function of R and whatever another scalar field would be to modify gravity. And formally transform that, and you can do that quite generally. And that then puts a multiplier times the matter of the object. So it also means that there are a lot of constraints from other observables associated with having such a modification of the matter of
But
the
you
object.
need to specify the field content of your theory to do that. Start with the Lagrangian.
No, the field content of my theory, apart from whatever's modifying gravity, is cold dark matter.
I know,
Maybe
but
cold dark
that's
matter
what I'm
varies.
saying, the bit that's modifying gravity. In this, you don't need to write
Yeah,
it
I
down.
know, but you might be able to treat the functional, that basically the scalar field gets, or the effective scalar field is completely locked into the conformal transformation factor, and that's now got dynamics associated with it. That's at least a reasonable thing to look at.
No, but like I say, I think that's sort of coming up the problem from the opposite end. So that's saying, how can I parameterize my models? Whereas this is essentially parameterizing the data in some sense. So people have written down things like the growth factor gamma.
Okay, good, right, all right. It's within that context that you're working with.
Yeah.
But then, so you're not necessarily modifying gravity.
Exactly. So you could write
This
sort
is
of.
warm neutrinos.
Yeah, but you could write that in terms of mu and eta. So at the very least, what you've got is if you see them not equal to their GR value, then you've got some breakdown of something. And what you would do then is using the principle of analysis, you can get an idea of the scales and redshifts and so on, that's what's causing that breakdown. And then that should give you a clue as to whether it's massive neutrinos, whether it's a particular theory of modified gravity, whether it's whatever.
Okay,